I'm here today because we did this crazy thing in the lab. And the crazy thing was to use this 40-year-old tool called Make to do neuroimaging workflow. And so I'm happy to talk to you about this today because I think it's really fun, and Dan was a co-author on this paper. So this is if you just Google Make neuroimaging, there's probably nothing else that comes up because this is sort of it. So, and this is the Frontiers paper that we did, and it describes kind of why you would be interested in doing this, right? There's so many cool tools out there in the world, and for workflow, why would you use something that comes with the default Unix distribution and that is that old? And it boils down to some sort of simple things, and we also wrote a manual about how to all do this, and so I'll be going through some of the practical parts of the manual as well. So that you can find that manual if you look at the supplemental materials for that, or I posted the link to Slack a little bit earlier. So this is what this is kind of what a script for workflow looks like. But since you all use different sorts of neuroimaging things, and we'll just do it abstractly first and describe this, right? So this is a for loop in a pseudocode for making a tasty breakfast sandwich that I'll call a waffwich. The basic idea is that we needed something quick to eat in the morning, and I read some article about 10 really fast breakfasts, and one of them was toast 2 waffles smeared with peanut butter and put berries in the middle because jam has too much sugar. This was the approach, and that's what we did, right? So this is a shell script-ish thing that describes how you do this. So for each person, you toast the waffle, you spread the peanut butter on the waffle, you arrange the berries on the waffle, you cut it, you fold it in half, and then you are done. Right? So this is how most people script. Whether you do it in Shell or you do it in MATLAB or whatever it is, this is kind of probably how you do most of your simple workflows. The problem with this is that it doesn't provide the information that you need for 2 main things. It doesn't provide the information that you need, number 1, to run this in parallel, and it doesn't provide the information that you need to pick up if one of the steps fails. There are many places in neuroimaging where steps fail, or where you need to do hand correction. I mean, if there is one person among you who has had perfect skull strips every time, please come to me and tell me your secret, right? We've had to fix, we've had to redo, all sorts of things, right? And once you do that, you have to redo every other step of the pipeline subsequently, right? So in order for any workflow to be useful from these perspectives, to get things done fast and in parallel, and to pick up when things break, to be fault tolerant, you have to express the information that you need to accomplish those 2 things. So it really doesn't matter what language you choose, but that is why when thinking about this problem several years ago, my mind went immediately to Make, because Make is a Unix utility for exactly that purpose. The idea behind Make is to express a pipeline of stuff that you have to do as a graph, as a dependency graph, things that depend upon other things. And that's every single neuroimaging workflow that you have. Right, so let's go to this example and then just look at what that looks like as a dependency graph. So if we look at this as a graph, we can see that here you express the fact that you have your waffwich is your target, your final target that you want to create, and it depends upon the berries, the peanut butter, and the toasted waffle. And the toasted waffle is a state of waffleness that is dependent upon the waffle, okay? So this expresses these things. It also means that you can go get the berries from the fridge whenever you want to. You can get the peanut butter out from the cupboard whenever you want to. You can toast that waffle whenever you want to. The only key thing is that they all have to be ready before you can assemble the sandwich. Right, so this is the essence of describing the dependencies inherent in workflow. And you can see that that shell script you wrote, or we wrote, whatever, that script does not have this information in it. It doesn't give you this sequence of how you can do things, that you can rearrange the order of them, and to know that if you burn your waffle, you have to go pick another one out and restart from there. But you don't need to worry about these other parts. Okay? So that's kind of critical, and so you need some sort of language that will express that. So Make is built precisely to express that. And this is sort of a make-file-ish syntax of how you write these rules to express this graph. And it looks something like this. So your WAF, is your target, and it depends upon these things. And then it has a recipe for exactly what you do. Once you have those things in place, this is how you assemble your WAF. This is a little bit of code that you use in order to create the WAF. Right? And similarly, for the toasted waffle, it depends upon a waffle and you toast it. There are two rules here, right? So that is how make allows you to express this information in such a way that you can then build that dependency graph, or that it builds that for you, and then it can do two things. It can parallelize your execution automatically for you, and it can recover from errors or changes to files. So let me switch to real data then, actually, right? So I have very simple pipelines made up, and these are things that I did for practicals that are available to you. This data and this whole tutorial is available. But if you want to look at it now, if you log into IT, it's in my home directory, which is Madhyastha. And I have, you can copy it to your own directory, but I have two example sorts of data sets. One is that we're looking at right now is sort of a cross-sectional data set. This is kind of the processing that occurs, for example, if we have a bunch of FLAIR images or something like that, we want to do white matter hyperintensity quantification or something like that, it only relies upon the FLAIR image, so all you have to do is apply a sequence of things to calculate those images that are, that quantify the white matter hyperintensities, and you might just do that all in one directory. The other type of processing that we have is sort of a more complex longitudinal pipeline where you have subjects with multimodal acquisition, and for each one of those modalities you have a bunch of stuff you do. Is this similar to what people do in general? Yeah? Does anyone have another use case thinking about something that doesn't fit into one of these two models? You organize your data in directories neatly, right? In some way. You have to have some sort of naming convention even if you're writing a script, right? So we have to do that here too. So this is just a simple case. Everything's dumped into one directory with a bunch of subjects. So this is from the OASIS data set. It's a structural longitudinal data set, and here I'm just taking a cross-sectional sample of different subjects. So we have a bunch of people, and we have the raw structural images. And let's say we want to do something to them. The very simple thing is we'd like to skull strip their brains, okay? So if I look at one of these, I will see that it is not oriented according to FSL's conventions. If it loads. Please load. So I'm going to need to reorient these first. Yeah, so otherwise skull stripping will fail pretty miserably. That was one of the first things I discovered about neuroimaging. So that's the first thing that we have to do, and then we have to run that. So let us write a little make file. This is makefile.1. It's too small. Options. Okay. So what we have here is we have the format where we're skull stripping one person. We list the target here, and what we want is the skull stripped T1 image. We give it a nice name, and then we say that it depends upon the T1 image, and we run bet on it. To get the T1 image from the raw image, we put that file list there, and then we say it depends upon the raw image, and then we do reorientation of it, right? And I have some funny symbols here. Make is got a very bad reputation because it has all sorts of crazy symbols. So this here, this $ less than sign, what that means is the input. So I can just rewrite that and say OAS to 0001 t1.nii.gc. And then the target is just that, right? So that's the same. So everyone's familiar with that back command, probably seen that. So that's very simple, right? But that's kind of just a lot of typing, so that's why people shorten that and just say instead like that. So $@ means the target, that's the skull strip file, and $ less than means the dependency, the input. Yep. So already, having learned this is the one of the sort of really confusing things. Why does everything in Make sort of look like splats and blashed and weird things, right? Well, it's because people couldn't type, so had to make shortcuts for everything because there's no sense in typing things over and over again. Didn't have very good editors. So the next thing back there, hopefully you can understand that this is taking the raw data, and it is going to reorient it to produce the T1 image. Okay, so let us see. This is just for one person. I saved that into Makefile1. To run that, if I called that Makefile and I just said make, it would be fine. But otherwise, since I want to save it as Makefile1, I can say make-f, Makefile1. That specifies where I have my commands, and it should go and do things. Now remember that my reorient command came after my skull strip command. That order doesn't matter. What it's doing is it's looking at those rules and it's creating a graph. Okay, so it doesn't matter what parts of that graph you put in where, it will assemble that for you, which is a cool thing, because if you actually ever take your workflow and you try to draw a graph of it, has anyone done that for a paper? By hand? No? No workflows for... It's really hard to draw your workflow. I mean, how often do you get that wrong? I get that wrong all the time. You forget things that are there. So this is a difficult thing to do, and so it will put that together for you just by virtue of one rule at a time, which it means you have to use less working memory to keep that pipeline in head, right? You just think about one step at a time and it will put it back together for you as long as you have a consistent convention for your extensions. Okay, that's fine. We did one subject, but who cares? That's one subject. We have to do all of these subjects. And the last thing that I want to do is type in all those rules for all of those subjects. I could, but that's a big pain, right? So what I'm going to do is I'm going to make it so that I'm going to walk you through a Makefile so that you can do it with everything and explain how that works. Okay. Everybody's so quiet. Questions? No one cares. You're just sitting here for dinner, waiting for dinner. No? No. I feel free to ask questions because it's going to be more relevant if I address the things that are most, that what you're going to use. It's probably been a long week. Okay, so often we have many subjects, right? And so we can set variables in Make, just like with anything else. And we can also invoke shell commands. So subjects here is a variable, and what we're doing is we're saying we're going to cat a file called subjects. I often like to so there are many ways you can get a list of subjects. If you feel like using patterns, you can use the patterns in the names, and you can extract that. You can dynamically pick up whatever. You can refer to another directory and get the names from there, whatever happens happens to be there. That's nice, like for example, when somebody puts a new T1 image, new directory, and you want to just do all the processing for that person, you can refer there and just automatically pick up new subjects. But I found that what's kind of nice, especially for established projects, is to have a fixed list of subjects, because you kind of just want to know who you're dealing with and don't worry about errors caused by that person who has the missing, whatever it is, the missing B0 field map or something. You can't do their resting state processing, whatever. You just want to know who you've got in and keep that be the same. So I often just like this one. I like to just cat a file called subjects, which has a list of subject IDs. Very easy to make, and then you have it for all different purposes for scripting. Okay, I will skip over the phony right now and just show you what the skull strip target looks like. Here, we want to do the skull stripping for all of the subjects. So what we do is we use a sort of a pattern replacement thing that Make has. All of these things, by the way, they're built into Make, which is in every Unix system. And so you can say, GNU Make manual, and it will have a relatively short, 100-something pages, I think, manual that goes through all of the different things you can do in Make. So this is not, it's well documented, which is a nice thing. So here what we're doing is we're taking the subjects variable and we're replacing this colon equals means take every subject and then basically replace its string with equals, add to it, underscore T1 skull strip. So that's just forming a list of skull strip names. And you do that, and that means that skull strip is like a little fake target that's leading up to our phony. It's a convention, a naming convention, because then I can say make skull strip, and it will depend upon all of these subjects being skull stripped. All right, now, phony targets. Let me speak a little bit about phony targets. Normally, what Make does is it's comparing a file name to another set of file names, and it's looking at the date stamps on those file names, and it's saying, well, is my target newer than all of those things it depends upon? Or maybe my target doesn't exist, and I have to create it, right? So it has to exist, and it has to be newer than those things it depends upon. And then it will fire that recipe. So what you have here, though, is a situation where we want to have a shorthand for all of those subjects whose names we don't know. We pull them in from a file. So this is called a phony target. Skull strip. It depends upon all of these things. But if somebody just wanted to go and screw with Make and create a file called skull strip and just leave it around in that directory, and if that were newer than all of the T1 skull stripped images, Make wouldn't fire, right? So we have to have some way of telling it, this is a target, but it's not a real file. Don't look at a date stamp for this file. Don't care if this file exists. It's a phony file. It's a phony target. And so that is what we do with the phony target. So we say here that phony, this is a special meaning to Make. Skull strip is a phony target. And so is clean, by the way. Clean is a little cleanup thing, right? We're always short of disk space. Always, perpetually short of disk space. So one of the nice things to do is clean up after your pipeline, clean up partial products that you don't need, clean up miscellaneous backup files that you may have created, all sorts of junk. In this case, we clean up everything and restore it to its virgin state so that you can just type Make again and go, and with the ultimate of reproducibility. I don't think we're really there yet. That's where we'd like to be. So there's often a lot of little cleanup targets, like mostly clean, archive, something like that. But basically, it's a phony target that actually executes a recipe which just removes junk. So phony, that's the phony targets. Now let's get to the patterns, right? So we often have the situation where many files fit a pattern. Many subjects fit a pattern, or sometimes I have a colleague who's working right now with doing probabilistic tractography. So all of his seeds and destinations, all of his tract files fit a pattern that can be substituted by putting in different regions of interest, and thus create all the file names that he needs to create. So the way that you say that something that matches a pattern depends on something else is you put a percent, and that's the pattern character. So here we have percent T1 skull stripped depends upon percent T1. Right, so this is going to match the subject identifier here and here. And then we've got our, now you can see why our little shorthands come in so super handy, because we don't actually know what the name of this is going to be. Right? It's going to fill in for whatever subject we're trying to create. And so now bet, and then using the little $ less than and $@ here is super, super handy. It allows us to do this without having to worry. We can, of course, figure out what matched this part in here. We can use a $*, for example, to match that part of the pattern that was matched up here in the recipe. But here you can kind of see why these things become useful. Maybe it's not just for typing. And similarly here, we do the same with the raw, right? So we create the T1 by reorienting the raw image, just like we did before. And then we have the clean. Right, so this is more complicated, but what people typically do is copy a file from one project that has worked to another and modify accordingly. So let's see how this works. I didn't talk about the secondary. I'll explain. Okay. We only have 4 cores on this machine, so we're not going to try to do more than 4 things. Let's see. I often test makefiles by seeing what they will do by saying make-n. And remember, we're working on makefile.2 right now. Okay, and you see that it's going to go through and do the reorientation and bedding for everything all at once. So let's do that, but let's do that in parallel. And I'll say make -j4. I've only got 4 cores. -j tells you how many cores to use, and then you can go. So you can see that it's firing up 4 things at a time and going through. So while it's running, let's talk about secondary here. I commented this out, right? So here, this is one of the more complicated and subtle things about make. When you match patterns like this, what happens is that this can be a desired effect or not desired effect. It depends what you want. Notice that what we're trying to create are the skull stripped images. That's what we want. The reoriented T1 images, or sorry, the T1 images, which are the reoriented raw images, are just a byproduct on the way. So what's going to happen is you will see that they will get created because they have to be in order to do this processing, but then they will be deleted at the end because they're not specified as targets that we actually want to create. This can be good because it saves space, avoids having unnecessary things along the way, or it can be really confusing. So normally I vote on the side of really confusing. The way you fix that is you say that you either specify that you want to make those things as well here. You can put them in the target. Or you can say secondary. These are things that will be produced along the way and I want to see them. So in neuroimaging applications, those kinds of things are things like your 4D resting state scans that are registered to standard space. You probably want to look at them or some image derived from them at some point to make sure that that's correct, but you don't want to keep those around, otherwise your disk will become pretty full. I harp on the disk space. It's a big problem for us. So if we look here, we can see at the end this remove command, right? All of these T1 images that were created in the process of this pipeline are removed now, right? I can create any one of them that I want. by saying make, and then to make them. So let's just take, I'm looking at 0014. So I can recreate it simply by saying to make it. There is a rule for it. It matches that pattern rule there, and it will know how to recreate it. Likewise, if I removed something here, let's remove the 46 skull strip here. And if I do make dash F again, it will recreate my bedded 14 image and then redo the 46 one, right? Sometimes I forget what has to be recreated because it's kind of hard to keep track of that. So every time make catches me by surprise, it means that I would have made a mistake. So that's a lot. So it's helpful because if you modify something, sometimes we have problems, for example, that you need to reconvert the DICOMs or the PAREX or something like that. We're a Philips site because one of the conversion processes didn't work, and then you have to rerun everything from there. So this way your images will have new timestamps, and then everything will resequence from then on. Yep. So that's good. We talked about doing it in parallel. Let's look at that secondary issue here. If I uncomment that, then there's nothing to be done because all of them exist. If I remove all the skull strip ones, and then do that again. I'm not gonna, why shouldn't I do it sequentially? No. We'll just do that. Then it will recreate everything and it won't delete those partial products. Okay, so at this point, so you've sort of seen how this works. I showed you with a very, very tiny pipeline, but I think you could kind of see how you could expand out from that to add more complicated things for. So are there any questions at this point about how to handle a single subject kind of directory situation? It's not that hard, right? You can have recipes with multiple lines. One of the tricks, if you do that, is you need to separate them with a backslash and a colon. More strangeness. The reason for this is that each line of a recipe is treated independently. It's like as if you run it in one login shell. And you know what happens when you run in a login shell and you set like an environment variable or you set an environment variable or a variable or something like that, and you bring it up another login shell and those variables don't exist. It's the same thing with make. Every line of your recipe probably depends upon the previous one, or it might depend upon some variables that you've set. So you want to make sure that they are set. So technically sometimes it'll work just fine if you don't do that. But more often than not, you actually intend to set some variable in your recipe that you will then use later on, and that's the time it's going to get you. And so as a matter of habit, what I've just typically been teaching students is just please always connect all of your recipe lines so that they are all executed in a single shell. Right, so that you can just simply do that. By basically here, if you have another line there, you just put a backslash and a colon, and then colon and a backslash, semicolon, yep. Sorry, and then you go to the next line. Okay, so are people interested in talking about like a more complex longitudinal situation, or, yeah? Okay. All right, so the data here are, there is an example. So here, the example is OASIS longitudinal sample small. And this is how we organize a project that has multiple time points. And we always assume that a project is going to have multiple time points, because because once you've collected one set of data on a set of people, invariably it's great if you can get them back. So even projects that don't intend to be longitudinal often end up becoming so. But we also have many longitudinal projects by design. So I work particularly in the ADRC and the UDAL for Parkinson's disease and for Alzheimer's disease, and we take people multiple times and look at them. So this is how we set things up. We have in this directory, we have like a bin directory, which is where we keep our executables and our scripts and things like that, stuff that is particular to the execution of the pipelines for this project. Usually there's a free surfer directory. We run free surfer on most all of our subjects, and so that loves to have its own organization, right? So people here use free surfer? Yeah. It wants to have its own organization. You don't mess with its organization. This is another thing that I've learned the hard way, is you do not try to wrestle a neuroimaging program into doing something different unless you want to maintain it for the rest of your life, and I don't. So that's what we do. We just work with them. So there's a lib directory. Lib is for like masks, for make files, for reference things. You know, sometimes there's particular atlases that may be relevant for a particular project. So we're just taking the Unix conventions and trying to organize our things in findable ways. But then what we have is we have two directories where we have subjects, and then in each subject directory, we can see that we have a visit 1 and a visit, or visit 1, 2, and 3, depending on how many visits. I structured this from the OASIS and kind of removed a bunch of visits to make it a little fun, you know, so that we could sort of have some more exercises based on that for different purposes, you know, counting the number of visits and figuring out what's what. So that's how that's organized, so that there's a subject directory and then a visit directory for each one. And that's kind of like the standard way that data are often distributed. But then what we do is we have a visit 1 directory here where we can have a cross-sectional view of all of the data. What this is just a little make link script that will make symbolic links. So what we can do is create a symbolic link to the previous directory structure so that we can find everything. I know this is probably already sounding convoluted. Did that not work? Okay, so, but the reason for it is this. Make likes to do, it can do recursion into directories. So what we're basically trying to do set up here with a longitudinal thing is we try to set it up so that we can process all of the data for each time point of subjects, for all subjects in parallel. But usually data are coming in one time point at a time. So you're getting a few subjects for your first time point, and then a few subjects for your second time point, and so on and so forth, right? So we have found that it's easiest to set it up so that you have the data in both formats. You keep it in the sort of the deeper data format where you can look at each subject and what time points it has, and then you can also look cross-sectionally at each time point and do cross-sectional processing that way. So this design came from working on the Seattle longitudinal study, which has about 160 people imaged over 4 and probably now 5 occasions, 2 years apart. So that's a kind of a lot of data to handle, and that was based upon that model of let's do cross-sectional analysis as often as we can and longitudinal analysis as often as we can. And so after trying a variety of things, this is what I had come up with as a reasonable thing that worked well also with Make. So what you do here is you do your processing in the cross-sectional time point for your data. And if you only have a cross-sectional study and you know that you're never going to have more, then you don't really have to worry too much about the longitudinal aspect of it or anything like that. But it's just to show you that it will scale. So what you need is 2 make files. You need one that is going to be running your for loop, essentially, across all subjects. And then you need one that's going to be just like the one I showed you, which does the processing specific to that subject, where you don't care about the subject ID or anything like that. You know what your files are named and things, and it's all there. Does that make sense? Yeah. The only thing is that you have no concept of a for loop in Make. Everything is a dependency graph. Right? So your dependency graph means that your target, make all, is basically like an all with, I'm not sure that I have a pen. Yeah, I do have a pen, maybe. So you basically have a dependency graph where you've got your all, and then this is S1, S2, S3. And they can all occur in any order you want. Right? They can be done however you want. It's just that to do the all target, you have to do every single one of them. Right? So again, no for loop. It's not a for loop. So this is what it does look like. So here, this is the little driver make file. What we have is, again, just like we had before, we do the same kind of wildcard or same sort of something to get a list of subjects. And here I just used a wildcard. This just show you that there's many ways of getting a subject list. We have 2 targets here, only one of which is really important, because you have to put a make file into each directory. That can be a symbolic link, right? So that's fine. So let's not worry too much about that. That's what that is doing here, is creating symbolic links. But you can do that with a program. You can do that anyway. You don't need to do it in that way. But the key thing that is difficult is these 2 lines here. So if you're doing your phony target all, the key thing that you want to do is you want to do all your subjects. You've got to do some sort of subject level processing. Then for your subjects, right, this is as if you said subject 1, subject 2, subject 3, I forget what the actual numbers are, but all your OASIS subjects, it's as if you listed them all here, one after the other. When you have multiple things on the left-hand side, what that means is that it's like having many rules, right? So it's like having this rule repeated for each subject. So what we do here is for each subject you call make recursively. That's what this $capital make in parentheses means. It's a recursive call to make. So with the same arguments that you've given it, it will call itself. But also it will call itself with a directory, and that directory is what's $@? The target, the directory. So that's the subject directory. So it's going to go call itself within the subject directory, and then you give it a target. So you have to call a little bit differently at the higher level. So what you do is, at the top level here, what you would do is you would say make target equals all. And then let's just do make dash n and see what it would do. Okay, so it goes in there and, okay, first it's linking up all of the subdirectories, which it does. And then it has no rule because I just made the subdirectories. I just made the make files in there. And then maybe I don't have a target for all. Oh, no, my target should be skull strip. So if I said, so I'm sorry, so if I said make dash n, then what it would do is go in there and it's having problems. Why? Oh, I didn't actually put the make files in there. All right, that's why. Okay, now I actually did it. I put the make files in there, and now you can see if I do make-n all, you can see that what it's going to do is it's going to go into each of the subjects, and it's going to go and it's going to execute make inside that directory. And it's going to do that reorienting and that skull stripping that we did before. And it's going to do that for everybody. So that was the test run, the -n. If we can do that for real. And go and do that. So and remember, the nice part about this is that it's doing it, but if there's a problem with any one subject, you can pick up and do only that, right? So you don't need to go and hack your script and remove that subject ID out of that and rerun for just that subject and copy things out, because, you know, even with GitHub, to keep revisions of those things, that's kind of an error-prone sort of process. So this is a little bit closer to the ground and expressing things a little bit more like what they should do. So questions? This is like the whirlwind introduction to Make.
Having used Make for a little bit now, some things that are non-obvious that make things really, really easy is that targets, even phony targets, are available with tab complete, which helps things a lot. And also Make files can include other Make files, so things can be really modular, and you can just staple different bits of analysis pipelines onto each other as long as the naming convention is consistent. And also there's a lot of annoying logic that sometimes you need to put in bash scripts, like, is this file here before I start running this script? Or is this part of this script already, or is this part of this processing already been done, so I'll just take what I have so far and bring that forward, and all of that is just taken care of.
So along those lines, I can show you, like we use this to organize, I think, most of our projects in IBEC now for a while, actually. And so this has led to some of the undergrads who work with this developing some tools by requests that will make life a little easier for us. And one of the things you can do is you can have, you know, different scripts make files for different processing pipelines. For, like, for example, your DTI pipeline for a particular acquisition, for your structural registrations for a particular acquisition, functional, that sort of thing. So this is one thing that one of my students made up, which is a work in progress, but what we wanted to do when it becomes complex, one of the problems people were having was figuring out, number one, when you have a file that's been created, where did it come from and what generated it? And number two, you know, what makefile do I look in? If there's 5 different makefiles for the different processing steps, that becomes kind of a lot to look for, and it's a little difficult to just grep through them because of all the pattern matching and things like that. So this is what he generated, and the directory structure is like I showed you for the ADRC project here. It's just filled out a little bit more. This is not generated. This is a description that is put in. But the variables here, these come from, this is an auto-generated file that comes from comments that you put inside your makefile with specific tags to indicate what they are. So this is really super helpful. It tells you what, what path you're working with. For example, path will tell us, if we know our architecture, we know what versions of the files we're working with, what programs. ANTs, for example, we know that's advanced normalization tools, and we like that for registration, but there's a bunch of different versions that people are using. I've made this mistake before, 2 different standard brains, 1mm and 2mm, with both standard in the names, so that kind of helps a bit. And then for the files, this is the naming conventions that we use. This has kind of like been one of those things that sort of, yes, you should write down your naming conventions. You should have all this information. But somehow it just never got done. So it's very much nicer to have this be part of the schema so that you can generate this with the comments right by the workflow that makes these files. And it makes sharing things with people a lot easier, because you come back to a project, 6 months later, and somebody's saying, gosh, I'd love to work with you. I just need, the data from the resting state acquisition that has been processed, but no smoothing, you know, all the motion correction and everything, but no smoothing, and I would like that. You're like, oh, where do I start? How do I make that? Like, where does that come from? And do I have it already, or do I need to write a new pipeline? And you can see where you can just add another recipe to an existing pipeline for one file, starting from one place and then just bringing it to a different place, because, you know, often you're looking at people doing different types of sequences of transformations to data and to do different types of analyses, and so that's kind of useful. And this has the directory of all the different types of things that for the small starting workflow, and then the targets, so you can refer to these targets and do these kinds of things. So I like it because I never remember the syntax of the commands, so it helps me. And then I can see how they're called if I say make-n. Any more questions?
What is .mk file?
An MK file is just a different syntax for makefile, like a different naming convention. If you put .mk, it's just an indication that it's a makefile. And so makefile, capital makefile, has a bit of a special designation. So the first thing that a makefile, when you type make, it's going to look for something called makefile. As we showed with these examples, you can call it anything you like and say -f and then give it that name. But since we like to parcel out and make more modular our makefiles, our different processing streams, we call them something that's descriptive .mk. And that's what this is. So prep subject, structurals, QA reports, things like that. These are all different and often written by different people. So that's pretty nice as well, is that then it's a little less coordination required. You can hand it off to the person who's the expert in ASL or DTI or something, and then they can do that part.
It looks like a lot of the MRI tools that you're using work well with Dash, but could you run functions from SPM or anything to be able to?
Yeah, so I had that question Monday. So if it depends. SPM is a bit hard because from what I understand, it's difficult to compile anything from there, right? Yeah, so that doesn't work very well. If you're very tightly in SPM, then you're kind of embedded to parallelizing within MATLAB and doing any sort of, are you able to parallelize outside?
Yeah, I've done some like wrapper rig where it's.
You call it, yeah. Okay,
Yeah.
So you don't compile it, you just call it without the GUI or something like that. Yeah, so you can always do that. We have licensing problems with that, so like I don't think right now we have enough licenses to actually do that in any sort of cluster situation, although that may have changed. But yeah, I think that will work. That will absolutely work fine. But yes, and this is very geared towards having a Unix programming environment where you have interoperable commands within that. But that said, you can mix and match your MATLAB. As long as it outputs something that can then be read by something else, you don't need to wrap anything. So you just need to call it, which is really nice because we don't like writing wrappers. Wrappers take a lot of time. All right then, thanks.